Hello everyone, welcome to the next part of this lecture. In this again we are going to do another circuit problem. We are going to look at a series RLC circuit, and we're going to make things more interesting by also looking at what would happen if we have a, rather than kind of a constant source, if we would have a sinusoidal source, right? And then we're going to transform the circuit in the time domain. And we are also going to look at kind of the interesting what will happen to it. Okay, let's get started. So here's an example where you have a series RLC circuit. Your resistance 4 kilo ohms, inductance 62.5 millihenry, and the capacitor 10 nanofarad are all connected in series. When the switch gets closed, the source V of t gets connected to the circuit, starts supplying energy. Good thing is no initial energy is stored, so we don't need to worry about the initial energies, and our things will become simple when we are going to model the inductor and the capacitor. Because we are not going to model it as a kind of a series and parallel thing, it will be kind of a very simple Ohm's law modeling where we can just represent them as an impedance. Okay, so let's get started. And again, here is the V of t. Your source is 15 volts times cos of 40,000 t, right? And the idea is to find the value of the current at t is greater or equals to 0. Okay, so let's get started. Again, I am gonna transform the circuit into S domain, and then I'm going to find the value of the capital I of S, and then I'm going to Laplace inverse transform this whole thing. So before we get started, let's get started. Okay, so before we transform, or in order to transform the time domain circuit into an S domain circuit, right? So we follow these steps. The first step is to find initial conditions. All right, so no initial voltages, no initial conditions that we need to worry about from the question. The second one is we transform the independent current sources, current or voltage sources, whichever are present in the circuit, right? So we have to find V of S, which should be the Laplace transform of V of t, right? And again, your V of t is, what is this? 15 cosine of 40,000 t. If you remember, the Laplace transform of cos of omega t, and you can get it from the tables, is equals to s over s square plus omega square. Okay, this is going to make my life simpler because this 40,000 is actually omega, and then I can easily write my Laplace transform of this v of t. Okay, so the Laplace transform of this v is capital V of s equals to Laplace transform of 15 cos of 40,000 t. So it should be equals to 15 times s over s square plus 40,000 square. Okay, and this is volt second. Okay, nice. So I ended up converting my independent voltage source into Laplace transform. The third step usually is whatever the current and the voltages values are present, or we need to transform them into S domain as well. I just have this I of t, right? This will be transformed to I of S in the Laplace domain. Step number 4 is we have to now actually transform the circuit. Since there is no initial energy stored for the inductor of capacitor, so I can model my inductor and capacitor by simple impedances, right? So I'm going to find first ZL, which is SL. Again, you get S times 62.5 millihenries, so this is going to be in ohms. You can further, for example, 6.62.5 10 to the minus 3 should come out to be S over 16 ohms. Interesting. Let's find ZC as well. ZC is 1 over SC, which is 1 over S times capacitance, 10 nanofarads. So it can be easily written as 10 to the positive 8 over S times ohms. Okay. Okay, so I got everything. Now let me make a S domain circuit. S domain circuit. My S domain circuit again is going to be starting with my voltage source in the S domain, which is 15S over S squared plus 40, it should be 40,000 square. 40,000 square. Again, this is in volts second. Then my capacitor and impedance ZC, which is 10 to the 8 over S ohms. And then my resistance, which will remain 4 kilo ohms. And my inductance, which will come out to be, what was that? S over 16. S over 16 ohms. So this is my S domain circuit for time t is greater or equals to 0. Nice. What I need to do now is I need to essentially solve this for capital I of S. And then I have to find the inverse transform as well. And again, just by the looks of the circuit, it's simple, right? The kind of the Ohm's law in the S domain, where we're gonna have I equals V of S divided by Z of S, right? So for example, I can easily see that it should be something like this, right? Where Z of S is a combination of this, this, and this. Okay, so let me find this value again. I of S should be V of S divided by Z of S. So V of S is 15S S squared plus 40,000 square. 15S over S squared plus 40,000 square divided by resistance is 4 kilo ohms, 10 to the 8 over S and S over 16. Right, so you have 4 kilo ohms is 4,000, 10 to the 8 over S plus S over 16. Okay, so if you were to solve this thing, I of S, you're going to get the following expression. 240 S squared divided by S squared plus 40,000 square times a quadratic expression, S squared plus 64,000 S plus 16 into 10 to the power 8. And again, this is ampere second. Perfect. So this is my expression for the I of S. Again, my current in the S domain. And I need to find this thing. Of course, I need to find I of t. I have to take an inverse Laplace transform. Before we do that, sorry. We do kind of an intermediate step where we apply the initial and the final value theorems and see that things are still making sense and our expressions are kind of correct. We had kind of implemented this as kind of a sanity check. So we can still do that over here. I'm going to start applying first initial value theorem and then the final value theorem. Again, initial value theorem, if you remember, that has to do with how to calculate the initial value of I of t in the time domain, in the S domain. In the S domain, the initial value can be calculated by taking S approaches to infinity. Again, the initial value is in the time domain. In the S domain, we do that by taking S approaches to infinity, if you remember the theorem. S times I of S. Right, so if you multiply S to this equation, you're going to get 240 S cubed divided by the same denominator, S squared plus 40,000 square, S squared plus 64,000 S plus 16 times 10 to the 8. Now the problem over here is, as you know, that if I'm going to put S equals to approaches to infinity or S equals to infinity in this equation, I'm going to get infinity over infinity, right? So I cannot solve this. And we have done this a few times now, how to solve this, right? So I convert this limit S approaches to infinity by, I change this as 1 over S approaches to 0, S of I of S. In order to do that, what I'm going to do is I'm going to divide this equation by S squared, both in the numerator and the denominator. And so for example, you can also look at it over here, 240 s cube. So for example, let's say if I'm going to take s squared out over here, I will be left with 1 plus 40,000 s squared, okay, and then 1 plus 64,000 1 over s plus 16 times 10 to the 8 1 over s square. Right, this s square, right, okay, so okay, so I got so 1 s squared comes out over here, and then I also took out, so I first took out s squared over here, and then I also took out s squared from the second bracket, so there should be another s squared here. So in the denominator I have s4. And again, this could further be converted into, right, so 240 s cube over s4 comes out to be essentially 1 over s divided by 1 plus 40,000 square 1 over s square 1 plus 64,000 1 over s plus 16 into 10 to the 8 1 over s square. Okay. Now you can easily see that if I would apply limit 1 over s approaches to 0, my numerator is going to become 0 divided by 1 plus 0 times 1 plus 0 plus 0, right? So you are 0 over 1 comes out to be 0. Okay, so I can also see that from the circuit itself, since there was no energy stored, so the value of the current at time t is equal to 0 should be equals to 0, right? So again, this should be equals to limit t approaches to 0, I of t. So this means that our I of s makes sense. Now let's see if we can apply a final value theorem. So the problem with applying a final value theorem, I'm going to make a kind of an interesting concept point over here, and we discussed that. You remember when we were deriving this expression of the initial and the final value theorems, we made certain assumptions. For the initial value theorem, our assumption was that we should not have a impulse function at time t is equal to 0, and then for the final value theorem, we made an assumption that our poles should exist in the left hand side of the plane and should not exist on the right hand side of the plane, because if they would exist on the right side of the plane, my solution will not settle down, and I wanted to settle down at t equals to infinity. Now the problem over here is that if you look at I of s, right, so I of s has poles at s equals plus minus 40,000 j, right? I have two poles. If I would solve this thing, right, I'm going to get two poles, plus minus 40,000 j. And the problem with this plus minus 40,000 j is this is going to create undamped sinusoid terms. And that is why I cannot compute my final value theorem, because, for example, one of these poles, s equals plus 40,000 j, lies in the right hand side. So this means that my solution at time t is equal to infinity is not settling down, and that is why or does not decay. For example, my oscillations are not decaying, and that is why I cannot apply the final value theorem over here. So just making a quick point why we only applied initial value theorem and not a final value theorem. Okay, cool. So once we did that, now I have to find I of t. Okay, so let's do the final thing. I am interested in finding my beautiful function I of t. In order to find I of t, I need to solve this I of s. And the problem with solving this I of s is I need to convert that into maybe partial fractions and then solve it. Maybe I can do that on the next slide. Okay, so my I of s function was 240 s square over s square plus 40,000 square s square plus 64,000 s plus 16 times 10 to the 8. Okay, right? Again, if s square plus 40,000 square has two roots plus minus j 40,000, as I've just shown you in the previous slide, so I can easily expand this as k1 over s minus j 40,000 plus k1 conjugate over s plus j 40,000. Now I have another kind of a quadratic equation of s. If you were to solve this quadratic equation, right, if you remember, right, minus b plus minus b square minus 4ac over 2a, you practically, the roots that you're gonna get is minus 32,000 plus minus j 24,000. Okay, so I can apply these roots as well and create the two more terms. Okay, so I'm gonna get k2 now, which will be s2, sorry, s plus 32,000 minus j 24,000 plus k2 conjugate over s plus 32,000 plus j 24,000. Okay, great. Now I ended up converting this IFS into partial fractions, and I just need to solve that. And I can easily, by the way, another interesting thing is that I don't need to solve for all four of these, k1, k1 conjugate, k2, k2 conjugate. I just need to solve for k1 and k2, and k1 conjugate and k2 conjugates will be just conjugates of those things, right? So only solve for k1 and k2. Okay, so when we solve for k1, and we have done this process many times, I'm not going to do it, but I'm still going to show you the equation. Right, here is the s minus j 40,000, so multiply both sides by s minus j 40,000, s minus j 40,000, and evaluate at s equals j 40,000. So once you're going to do that, right, you can see that if you're going to multiply everything by s minus j 40,000, and then evaluate at s equals to j 40,000, on the right hand side only k1 term will be left and all the terms will be cancelled out. So your k1 would be equals to 240 s square, and over here only the denominator term will be left, it will be the other one, because s minus j 40,000 will be cancelled in the numerator and denominator. So you are left with s plus j 40,000 times the other two things, s square plus 64,000 s plus 16 times 10 to the 8, and again evaluated at s j 40,000. Once you're going to do that, the value of the k1 is going to come out to be 1.875 into 10 raised to power minus 3. Nice. If k1 is this, k1 prime should be the same, because since it's just a real number, so the conjugate of the real number is just real number. There's no imaginary component here. Now let's find k2. Right, to find k2, again multiply both sides by this term, right? So s plus 32,000 minus j 24,000, and evaluate at s equals minus 32,000 plus j 24,000. Again, we have done these processes in the past. So what I'm going to do now, so once you're going to do that, again on the right hand side, so you're going to only be left with the k2 term, and the rest of the terms will be cancelled out. So you are going to get k2 equals On the left hand side, you're going to get 240 s square divided by, again, you get the whole thing, s square plus 40,000 square. And again, one of these things will be cancelled out. If you can convert them, factorize them into these two roots, then only this root will be left. S plus 32,000, J 24,000, right? S plus 32,000 plus J 24,000. And once you're going to evaluate it at S equals minus 32,000 plus J 24,000, the value of the K2 that you're going to get would be 3 again, put this value of the S in the numerator and the denominator and just solve the whole thing. You're going to get 3.125 times 10 to the minus 3. You're going to get a complex number, minus 126.87 degrees. Okay, so you got a K2, and interesting, K2 prime would be 3.125 into 10 to the minus 3. Modulus value remain the same, and your angle will be changed. So you got the value of the K1 and K2 as well. So once you find this value, you can easily get this thing now. So the value of the I of S now is, right? So the value of I of S is K1. K1 is this, 1.875 into 10 to the minus 3 divided by S minus J, 40,000, plus K1 prime, 1.875 into 10 to the minus 3 over S plus J, 40,000. Okay, now you're gonna be then you're gonna get K2 and K2 prime. So K2 is over here, this one, 3.125 times 10 to the minus 3, angle minus 126.87 degrees divided by S plus 32,000 minus J 24,000 plus K2 prime, 3.125 times 10 to the minus 3, 126.87 degrees divided by S plus 32,000 plus J 24,000. And I have to find I of t now. Okay, so let's find I of t. Before I find I of t, let's do this one step at a time. And so, for example, I know I can easily find the Laplace inverse of this and Laplace inverse of this. I'm going to start with these two, and then I'm going to come with the other two ones. Okay. So again, my first term is, why don't I call, okay, let me, am I using ABCD variables here? No. Okay, so I'm going to call the first term as A, the second term as B, the third term as C, and the fourth term as D. Okay, my term number A, again, my term number A was S minus J 40,000, right? 1 point, essentially you have to find Laplace inverse of 1.875 times 10 to the minus 3 over S minus J 40,000. Yeah, right? And then my term number B is Laplace inverse 1.875 10 to the minus 3 over S plus J 40,000. Okay, so again, you have seen this Laplace transform. We have done this Laplace transform, inverse Laplace transform so many times. So the inverse Laplace transform of this thing is your constant comes out 1.875 into 10 to the minus 3, and then 1 over S plus A is 1 over S plus A is e raised to power minus a t times the step function, right? Since you have a minus here, so we're going to get a plus there. Okay, so I'm going to get e raised to power plus j 40,000 t step function. And over here, I'm going to get 1.875 into 10 to the minus 3 e raised to power minus j 40,000 t, right? And the step function, I'm gonna add the step function at the end. Okay, now, so this is your A term and the B term. One interesting thing about, I can either write them separately, or I can, since I have these two terms are the complex conjugates of each other, so I can also use this identity, a raised to power j omega t plus e raised to power minus j omega t equals 2 cos of omega t. Okay, and if I were to use that, this means that my A and B terms are 1.875 into 10 to the raised to power minus 3 e raised to power j 40,000 t plus e raised to power j minus j 40,000 t should be equals to 1.875 into 10 to the raised to power minus 3 times 2 cos of omega t 40,000 t. Okay, so this term comes out to be 3.75 times 10 to the minus 3 cos of 40,000. Okay, great. So these are my A plus B terms. Okay, now let's do the C and D terms. Oh my god, C. All right, so if I remember correctly, rather than remembering, right, this is your C term. To make the life simple, I'm going to call this 3.125 and 3.125, both of these numerators as K2 and K2 prime. So C term is Laplace inverse of K2 over S plus 32 minus J24. S plus 32,000 minus J24,000, right? We just did this. So I'm going to get we just did this thing over here, right? I'm going to get a very similar thing over here. I'm going to get a K2 times e raised to power minus 32,000 plus J24,000 t plus J24,000 t. Okay. And similarly, I'm going to get a D term, Laplace inverse of K2 prime S plus 32,000 plus J24,000. Okay, so S plus 32,000 plus J24,000 should come out to be K2 static e raised to power minus 32,000 minus J24,000 t. Right, the difference in between these two expressions and these two expressions, right, is that both of these are in the A and B, they were multiplied by just a real numbers, and over here they are multiplied by the complex conjugates K2 and K2 prime. So we have to solve them, and I'm going to use another identity before writing down the final expressions. And the other identity that I'm going to use is, so for example, if you have a e raised to power, and you can easily, by the way, prove it as well, j omega t plus a conjugate e raised to power x minus j omega t, right? So this should be equals to 2 times modulus of a e raised to power x cos of omega t plus phi. And where this phi is coming from, phi or phi is coming from is a, these two things. A is modulus of a, since it was complex conjugate, e raised to power j phi. So based on this identities or theorems, you can easily calculate these two things. You can easily add them up, right? You can easily see that your A is K2, A asterisk is K2 asterisk, and then your X is minus 32,000, and your omega is 24,000. And you can easily rewrite this equation, right? So for example, A is K2, A asterisk is K2 asterisk, your X is minus 32,000, and your omega is 24,000. Sorry, it's only 24,000, not D. And interestingly, from the actual raw numbers of the K and K2, K and K2, I know that the modulus of K, okay, so let me write K2. The value of the K2 was 3.125 10 to the minus 3 minus 126.87. 3.125 into 10 to the minus 3, minus 126.87 minus 126.87 degrees. Right? So from this number, I can see that my K2 mod or A mod is 3.125 into 10 to the minus 3, and phi is minus, phi is an angle, so I can just directly write without the angle sign, minus 126.87. Okay, so I got all the the things done using this identity, and now I can just write down my equation. If I were to add now C plus D, right? So let me add C plus D. If I will add C plus D, these two things over here, the answer that I'm gonna get is sorry, 2 times this, right? Right, so 2 times modulus of A e raised to power x cos of omega t plus phi. So this should be 2 times mod of A is 3.125 times 10 to the minus 3 e raised to power x is minus 32,000. E raised to power x is minus 32,000 t. Oh, by the way, yeah, j omega t. And then you are gonna get minus 32,000 t times cos of omega t. Omega is 24,000. T plus phi is minus 126 angle, which angle? Minus 126.87 degrees. Okay, got it. So here's C plus D. Sorry. Okay. Wait. Okay. So this one was A plus B, and this is C plus D, and now I have to find my I of S. I of S, I defined it over here as AB, the summation of A, B, C, and D. And since I've already converted that into time domain, so I can just find I of t. Let me write it. Sorry, something is up with the pen. Laplace inverse of I of s, right? So I can write 3.75 into 10 to the minus 3 cosine of 40,000 t plus and multiply these two things together, 6.25 e raised to power minus 32,000 t times cosine of 24,000 t minus 126.87 degrees. And again, I was kind of missing the step functions because I said that I'm just going to add it at the end. And this is in milliamps. Okay. So this is your equation for the current um, in the time domain. Important thing over here is that if you look closely, that you have a transient response, right? So for example, this thing is making it go all the way down to t is equal to infinity. At t is equal to infinity, so this is okay. So there are like two responses over here. One is kind of a steady state response, and one is a transient response. And we're gonna look at actually this property in a more detailed way. For example, this one is more like a steady state. I'm gonna make this point in the maybe in one more example problem, and this one is a transient response. Because of this exponent, right, at t is equal to infinity, this is going to make this entire second term transient response 0, right? But this term, 3.75 10 to the minus 3 cosine of 40,000 t, is going to continue to keep on and on and on. And that is why t is equal to infinity. At t equals to infinity, this response goes down to 0. But at t is equals to infinity, right, this continues. And that is why your function doesn't decay. And yep. Okay, another important thing if you want to look at would be usually the steady state response in the final expression usually comes from the input, right? So for example, this 40,000 t, if you look more closely, is coming from these two poles, plus minus j 40,000. And these two poles, plus minus j 40,000, is coming from this thing, from this term, as plus 40,000 square. And this is coming all the way back, if I will go one more slide back, or maybe two more slides back, is coming from all the way over here, which was your s squared plus 40,000, right? Which was this. So in the final expressions, you may have a summation of the transient response and a steady state response, where the steady state response may come from the input, and that will continue, and a transient response yeah, may usually have this kind of exponents involved, and that usually goes away at t is equal to infinity. Okay, with that, thank you so much. It was kind of a long example problem, but I wanted to do that. In this lecture we may still go overboard, I guess, because yeah, I'm doing a lot of these problems. But yeah, thank you so much. Have a great rest of the day. Bye.